Okay, in this video we're going to use the Pasco spectrometer to analyse the light spectrum given off from a gas discharge tube. Okay, so this is the piece of kit here. This works wirelessly with the Chromebook, and we can use the Pasco spectrometry app to analyse the light in a lot more detail. Okay, so this is a fibre optic cable. Here's the light sensor here, and this is the tube, the gas discharge tube. I'll show you that in a minute. And this is the power supply, which I think you can read there, is 2.7 kilovolts. So you need a very high voltage. You need a couple of thousand volts to be able to pass a current through the gas that's in the gas discharge tube for it to give off photons of light. So as we know from the theory of spectra, when you pass an electric current through a gas, the electrons that are passing through the gas, they knock electrons in the gas molecules or atoms up to higher energy levels, and when they drop back down again, they emit photons of a specific frequency. So if you have a single element of gas, you should see quite a recognizable spectral signature, because only certain energy jumps or energy drops are available to the electrons, so only specific frequencies of photons are given off. Okay, right, now the tubes themselves, we've got a range of them. Okay, there's a few more here. Okay, oxygen, helium, hydrogen. Okay, this is what they look like. Kind of like a light bulb. Yeah, kind of like a light bulb, but they don't have a filament in them. Okay, they just have a gas. Okay, so you've got the two terminals, the electric current passes through the gas, so the electrons pass through the gas, knocking electrons in the gas molecules up to higher energy levels, and then when they drop back down, they give off photons. So that's the type of thing a gas discharge tube is. Now, I've had a play with oxygen, helium, hydrogen. Now they're very, very dim, a bit too dim for this sensor. Okay, the one, or the only one that I got to work very well was neon. Okay, so we're going to look at neon. We're going to look at the spectral signature of neon today. Right, so let's turn them on. Okay, so there we have the gas discharge tube is now giving off a nice, quite familiar glow. That's the sort of glow you get from neon lights. All right, and some neon lights have different colours because they have a different coloured coating that absorbs the photons from the neon and re-emits as different frequencies. Okay, well, hopefully you can see that glowing quite nicely. Okay, right, let's start recording data. So at the moment we've got background light. Just turn that off for now. I want to start recording data. Okay, so we've got background noise on the screen, background ambient light on the screen. Now if I turn that on, we can immediately see quite a recognisable spectrum there. Okay, now the beauty of this, you can go into UV, you can go into infrared, but we're really interested in the visible part of the spectrum. So as you can see from this neon light, most of the action is in the red end of the visible spectrum, which is interesting. But we can see these very obvious peaks at specific wavelengths or specific frequencies. So that's what we're going to do. We're going to identify, or try and identify exactly the values of wavelength, and then your project, your assignment is to use those values of wavelength and find out which energy jumps they represent in a neon atom. Okay, so works quite nicely. We turn the lights off as well. So let's turn the lights off. Let's adjust the brightness for you there. That should be good. So if we zoom, just stretch it out, zoom in a little bit, okay, we can hopefully identify the peaks more accurately. Right, now one of the features in this app which is nice, you can look at the reference lines. Now at the moment there's none set, but if that would be there, that would be a line for hydrogen, helium, argon, xenon, mercury, sodium, neon. Right, here's the reference lines for neon. This is what the app reckons neon should be showing. Okay, so this peak looks interesting because there's no reference line there. So I'm thinking that is an impurity maybe in the neon gas. If we go through, can we find anything? Maybe mercury. There's a definite line for mercury. That might be an impurity of mercury vapor inside the lamp. That's possible. So what we're going to do, we're just going to try and identify the wavelengths of definite neon lines. There you go. Right, so looking like this peak, looking like this peak is this one, looking like this peak is this one. Okay, I'm thinking this peak is this line here, although there's a slight discrepancy. That could be a calibration issue with the sensor. But what we'll do, we'll get the values of the wavelengths,